Now that we've looked at acids and bases, we can look at some types of acids that do not dissociate completely in water. These would be what we call weak acids. And weak acids, and what we call their conjugate base, are very important for something we call buffer systems. So these weak acids and their conjugate bases can comprise a buffer system, and a buffer system helps resist changes in pH. So let's talk about homeostasis again, going back to our homeostasis. If we look at blood, human blood typically is within a pH range of 7.35 to 7.45. So it is slightly alkaline. But this is sort of our normal operating range, our normal window of homeostasis for blood. If we get too far below this, then we go into what's called acidosis. And if we get a pH of blood that's too much above this, then we have alkalosis, or too much alkalinity in the blood. And both of these scenarios are very bad because then they start to have problems, or I should say proteins in the body start to have problems. They start to denature or unfold, and then they can't work properly. So one of the ways that we can resist a change in pH is to have a buffer system. So the body has several buffer systems, and I'm going to focus on one of them right now and just show you sort of how a buffer system works. So let's look at one called the carbonic acid bicarbonate buffer system. And we're going to make carbonic acid basically with carbon dioxide and water. So I'm going to write up carbon dioxide here. And carbon dioxide can combine with water. And I'll write it out so you can see it and you can see what these things look like. So it can combine with water to form a substance called carbonic acid. And this is indeed the stuff that you have in your soft drinks when you carbonate them. This is what gives them this fizzy. This is what gives soft drinks their fizz. But it's also what makes soft drinks acidic. And so I'm just drawing the components here. So we've got our carbonic acid over here. And you'll notice immediately that, like water, we have an oxygen with a hydrogen. So we've got a hydroxyl group here. This would be a hydroxyl group, and this would be a hydroxyl group. And just like water, we can see that one of these hydrogens could pop off and wander off somewhere. And it could leave its electron behind and become a proton. And as we know, an acid is a proton donor, or something that puts more hydrogen ion into solution. So this is exactly what carbonic acid does. And when it does so, it becomes bicarbonate ion. So this now is bicarbonate ion. So if we were to write this whole thing out, we would have carbon dioxide over here plus water yields carbonic acid. Which can become bicarbonate ion. And actually I'll take off this proton. And hydrogen ion. So this would be our buffer system. And the thing is, this reaction doesn't just go in one direction, it can go in either direction. So as the pH shifts in the body, then let's say we have too much hydrogen ion, well then our bicarbonate ion can take the hydrogen ion out of solution, become carbonic acid, which can then be broken down into water and carbon dioxide, and we can breathe away the carbon dioxide. So we can get rid of excess hydrogen ion in the body by having bicarbonate pick it up and then go back in this direction, so that we run the reaction in this direction. Now let's say the body is getting too alkaline. So then we can take more of our carbon dioxide and water, create more carbonic acid, and then we can release some of this hydrogen ion into solution. So the direction that the reaction goes in is going to be entirely dependent upon the pH. So that if we start to get outside of our normal window, then this buffer system will come into play and push us back towards our homeostasis, or to our window of ideal pH. Now let's write this out. Basically, this is writing the chemical formula for our chemical structures that I've written above. And so this reaction can go in either direction. And one of the things that we'll probably notice is this bicarbonate ion over here. Since it has a negative, it could accept another ion. So let's look at a common household cleaner also used as an antacid, and that is sodium bicarbonate. So sodium bicarbonate is basically bicarbonate ion and sodium. So this would be our baking soda, and this is what we use to clean the house. This is also an antacid. Some people use this as an antacid, so if they have too much stomach acid and heartburn, they might take a little bit of this baking soda. And so what happens? Now we're adding bicarbonate ion back to the body. So the bicarbonate ion can dissociate from the sodium ion and then pick up hydrogen ion that's in the body. So when you put this in here, the sodium ion will dissociate. And then this thing is free now to pick up a hydrogen ion and become carbonic acid. So it has taken the hydrogen ion out of solution, and then we can go back to our CO2 and water. So we could go back to water and CO2, breathe away the CO2, and basically reduce the amount of hydrogen ion in solution.